optimized Genesis sequence.
Mom, look, I'm in the movie. It's my first time presenting in the actual cinema. And this is very cool. I mean, probably those small, I don't know, movie was the most beautiful thing I saw in my life. Maybe it's just my adrenaline kicking in. Okay, anyways, thank you very much for coming. You already know who am I. And you see this nice generated picture about Spring and, I don't know, maybe Docker, maybe something else. Anyways, I will tell something about who I am. I am a developer advocate at Buildsoft. I'll tell a couple of words about Buildsoft a little bit later. I work 15 years on JVM. I just do not change this slide from my presentation to presentation. I'm too lazy. And my favorite languages are Java and Kotlin. At least they are languages I use the most, but I always had a chance to use Ceylon, Clojure, Scala even in production. And who remembers Ceylon? Cool. Lucky you. And of course, I used Spring a lot. Spring is probably the most popular framework. And yeah, it gives us very interesting tasks to master. For example, crafting an ultimate Docker image. You can find me by Asmodio in Twitter and by this obscure thing in Mastodon. I'm obligated to say a couple of words about Buildsoft. We are a vendor of Liberica JDK, and everything I'm speaking about today is reproducible with Liberica JDK or our own Linux, which is called Paketo Linux. We are the authors of ARM32 support, and it means that you can run things I'm showing today on ARM32 with our Java, but I cannot guarantee that they all work on different JDKs. Some of them will, some of them won't, depending on. And yeah, also Liberica is a runtime officially recommended by Spring. If you use Paketo buildpacks, I will talk about them a little bit later. They use our runtime by default. There are also numerous links to our site from the Spring documentation. Please look at it. Also, in the bottom left corner of each slide, you can see my Twitter handle. I will put the link to the slides in my Twitter after the talk, maybe an hour after the talk, because it will be hard. Anyways, we know our stuff, and let's jump to the main question. I'm guessing you came here to hear about an ultimate image, but what is ultimate Spring Boot application Docker image? Probably it's the smallest image, as small as we can go with a small GRE and small executable. But maybe it's an image with the fastest startup in like milliseconds. It's what Alina likes to show us, right? With GraalVM or with Liberica Native Image Kit, you build your Spring application and it starts up in no milliseconds. Or maybe it's something in between. I don't know what's ultimate for you. I don't even know what's ultimate for me, actually. So today, we'll try to look at all of them sequentially. But first, since we are talking about Docker, let's set up some common ground about it. First of all, I hope that everybody agrees here that each directive in Docker, like entry point, CMD, run, and so on, from creates a separate layer in the Docker image. All the layers are immutable. It means that if we add something on one layer, we cannot remove it on the second layer. And some layers can be zero-sized. And here's the simple example that we can create a Docker file, copy our application to our image, then delete the whole application. But the size of the image will be still, the last layer is zero-sized, but the size of our image is still the size of bash plus the size of our application. But okay, it's like a synthetic example. Let's look at something less synthetic. Let's look at something simple. For example, what is the simplest way to build a Spring application in Docker? It will be something like that. We take a JDK, Then we copy our application to the image. It takes some time. Then we run Gradle W build, or if you're a Maven person, then Maven package. And then we just put entry point inside our thing. Who likes, who thinks that it's a nice image? Okay, I'm glad not to see any hands. It's not nice, but let's look at its structure a bit. So there is a very basic layer of some comment. Then there are many layers of zero size, which add some labels and meta information. Then there is a 98 megabytes of our JDK. Then there is 67 megabytes of our application, because when I perform copy dot/app, I actually copy my whole application together with built binaries, generated code, and so on. And then when I call Gradle W build, it will be something like that. It will be 500 more megabytes, and then entry point doesn't wait nothing. Together with this very simple Docker file, we have like 580 megabytes changed on every build. Why do we care? We might care because push to our Artifactory or Nexus, if you use Nexus, is very long, and pull is also very long, and nobody likes to waste your space on spinning drives, even though it's cheap. If you have 200 commits a day, and every of them brings 600 megabytes of changes, it's a tremendous space you will waste, and you don't need it. So what is the easiest way to optimize it? So we can jump from this to something like this. Let's just build our application outside our Docker, and then we will copy our jar file to the we will copy our jar file to our image, and then in entry point or in comment we will run this jar file. And this is actually pretty good. Let's look at it. It was 67 megabytes of our application plus 500 megabytes of build stuff. Now it becomes just 59 megabytes binary, which is changed on each thing, on each pull and push, which means we saved 500 plus megabytes on every build, right? But now the build is not clean, because we actually don't want build depend on our environment or things like that. We have here we build something outside, and something can go wrong, and something will say it works on my machine, right? At this point, we can look at build stages. Who know about build stages in Docker? Less than half of you. I mean, that's very cool, because today you will learn something new. The simplest possible example of using staged builds for Spring applications will be something like that. Let's just take first image, and it will be JDK, and we call this layer, we will call this stage builder. We will copy our application to this builder, and we will actually build it with Gradle W build. And I skipped S here. Obviously, do not do it in your CI. It's not what you're supposed to do. And then we create a second stage. I named this runner just for convenience, just for easier readability. You can even skip the name altogether. But here you can see that we use GRE instead of JDK, which is significantly smaller. And now in the stage, I only copy a pre-built jar from the previous stage here. It looks like something like that. And our final image, already clean, because we do not depend on any environment on our machine. Everything is built in a clean Docker way. Everything is isolated. The structure of the image is basically the same, but now we have 58 megabytes of application, and that's all. I mean, we built an optimal image. Or is it? Probably we can go better, I don't know. Let's try. Let's talk about what are these 59 megabytes. Why are there 59 megabytes? Is there any way to optimize it? Actually, yes, because in some version of Spring, the feature of layers was introduced, and we'll talk about them in a minute. We'll change our Docker file again a little bit. We have this builder. It works the same way as it worked the previous time. It just calls Gradle W build. But now we introduce a new stage, which we call optimizer. In this stage, we copy jar file from a previous stage, from builder, to our jar. Then we change our directory, and then we call this magical command: java minus jar mode tools minus jar, our application jar, extract minus minus layers minus minus launcher. What it does, it actually gives us it splits application for us into different layers with dependencies, layers with our application, and so on. Now, when we need to run this application, we'll use JRE instead of GDK again. And we need to copy our layers, obviously, to our runner image. And we copy from optimizer, not from builder. We copy the layer called dependencies, the layer called Spring Bootloader, the layer called snapshot dependencies, and the layer called application. In this particular order is recommended by the Spring team. We can understand why. Dependencies, we almost never change them because, well, it happens, obviously. Probably we even change them each week or twice a week, but we change our code much more frequently, right? Then Spring Boot Launcher, it's another thing. It almost never changes, but it's not a dependency per se. We should launch it from a different place. Snapshot dependencies. Most of us do not have snapshot dependencies in their projects at all, but imagine you found a nasty bug in some library for whatever reason, and you submitted this bug, because you submit bug, you are a good developer, and you know that bugs need to be fixed, bugs need to be reported for them to be fixed by the third-party developers. And they fixed it, and they release a snapshot dependency for you to test it. And if it's a mission-critical dependency or it's a mission-critical bug, you want to change your dependency to snapshot. But snapshot dependencies have a tendency to be updated very frequently. They can be updated almost as frequently as our own code can be updated. Sometimes even more frequent. That's why we put snapshot dependencies right before the application, which is the most frequently updated part of the whole thing. And then we change a way in which we launch our application a little bit. Before that, we were calling java minus jar and then our jar. Now we call java and pass a class file we should call. It's a Spring internal thing called jar launcher, and hopefully it will launch. I promised to say a couple more words about layers. Here are they. There are actually two subcommands from jar mode tools. One of them is extract, which does this magical thing. It puts all the dependencies and launcher and snapshot dependencies in a different directories we can use later. But also, you probably want to know what's inside your jar. You just want to text all information, and for that, you can perform an action called list layers, some command, if you will, list layers. Let's quickly look what's inside our Docker image, how the flattened hierarchy of directories is structured. We obviously have our application. Then in bootinf classes, we have all our properties, banner.txt and banners.txt, DB migrations, and so on. Then we have this. This is from Spring AOP. We'll talk about it a little bit later, but Spring can remove a part of magic, a part of reflection from the application for it to perform better, to work better with CTS, and so on. Then we have our own classes, obviously, of our application. We also have these two magical files, class path IDX and layers IDX. They have all the meta information, what is where the classes should be located, where what layers consist of, and what layers are there. Then obviously there is a meta-inf, which includes, for example, native image meta information from all the libraries we use. Also there is sbom, which is sometimes needed. Then there is a directory with dependencies. It is kind of speaks for itself, right? It just contains many jars in lib subdirectory. Snapshot dependencies, which is empty in my case because I didn't use any snapshot dependencies, and Spring Bootloader. And together, my small application, it was almost a small Hello World application. In Docker, it takes 212 directories and 525 files. And if we will look into the structure of our layered application, we'll see that it basically consists of jar E, and then my dependencies take 57 megabytes, and then Spring Boot Launcher takes 382 kilobytes, and snapshot dependencies are empty, and my application weighs around 3 megabytes. And if you add them up together, then it's 61 megabyte. But 61 megabyte is more than 59 megabytes we had by just building the jar. What? Why is it better? How is it better? But here we should remember, what are we actually optimizing? We are optimizing not the size of image because it doesn't make any sense. We optimize the image of, we optimize the size of delta between two versions of our code. And our actual pull and push size on each build will usually be around 3 megabytes until we change any dependencies, of course. If we change dependencies, then it will jump to 61 megabyte. That's how it works. And at this point, we just reinvented how the Bellsoft build pack works. And it's amazing. When I say Bellsoft build packs, I reference build packs. There are cloud native build packs. You can Google them. They are located at Paketo.io. Do you know that IO domain can be gone in like several months because of political issues? It's a very interesting story, but definitely not for this talk. Generally, the idea of Paketo build packs is let's allow people not to write any Docker files at all. Let's detect the type of application and build the optimal Docker image for them automatically. This is how it looks like. It's pack, build, for example, pet clinic. Pet clinic will be just a tag of our image. With builder, here I use Bellsoft/buildpacks builder, but there is cloud native buildpack builder for Java. It works also. Then I give a path to my application. If I'm calling it inside the root folder of my application, it's right here. And then I pass one environment variable called BP-JVM version, which stands obviously for a JVM version we want to use inside our image. So we had to write like 12 lines of Dockerfile code, and this all can be replaced with one command with Paketo build, pack build. If we will look at the structure of the resulting Dockerfile, it will be something like that. It's 98 megabytes of jar E. Then there will be an application layer, which is dependencies. Then there will be our own application. They call it buildpacks application launcher. This is very nice that they tag images for us, the tag layers for us. It becomes much easier to understand. They also add some config on top. They say that probably people change configuration of their applications more frequently than they do their code. This is an interesting idea because usually we are trying to write our application like that. Let's make it not in code, let's make it in configuration, then we won't need to redeploy everything, or we won't need to rebuild everything. So they have their argument. I do my stuff the other way, but I like this one too. Hopefully you like it too. So quick summary about buildpacks. If you don't know about them, buildpacks transform your application's source code into a container image. It will be the Kubernetes compatible, it will be Docker compatible, whatever. It is very much like S2I. People who use OpenShift probably heard about S2I. But generally, yeah, it's a magical box that takes your source code and outputs the binary on image or whatever. And of course, they're Spring aware. So if you use Spring, you can use all these features of layers. But let's get back. Let's get back to building the ultimate image. Is this all? So we achieved the optimal pool size, either with handwritten, handcrafted Dockerfile or with Paketo buildpacks. I would argue that no, because optimization is multidimensional. What if we wanna faster start, not smaller image size and not pull and push, and we can sacrifice something to have applications that starts up faster. Just an example, I was experimenting with Spring some time ago, and I found a huge application called ThingsBot. It's an IoT thing. It allows some sensors and so on to send some data, and it builds nice dashboards and so on. It starts up almost 2 minutes. And I would say that I do not care at this point how big the image is. Please start up faster. Let's just imagine I need a cluster of these things. I need I need 1,000 nodes with it in my AWS, and I need a faster rollout. There are several techniques supported by Spring and supported by Library GTK and some other GTKs too, that allow us to cut some time from startup. First of them is called class data sharing. Who knows about CDS? Surprisingly, some of you know about CDS, but who knows that it appeared in Java 5? Okay, like three guys here know that it appeared in Java 5. Yeah, I was very surprised. It was very rudimentary, and the idea was very simple. At the times of Java 5, we were launching many Java applications on the same server. And we said, okay, probably we can cache something for consequent startups of JVM to be faster. And it actually worked, but it's not actual anymore. We do not do it like this anymore. We launch our application in virtual machines, in containers, and so on. And the idea was very simple. They took some data from JVM and they put it into an archive, something.jsa. And it allowed Java to start up faster. How does it help us? It actually does not. But in Java 10, the concept of application class data sharing was introduced, which meant that now not only JVM, but also an application data can be stored in this JSA archive, which is actually better. Let's imagine that we launch an application, then we run our load tests on it and something like that, and then we save all the data to a JSA archive. We could reuse it on consequent launches, and our application would actually start up faster. It still wasn't very convenient to use because nobody wants to launch their. Not everybody even has a load test in their pipeline, which is perfectly fine. It's better to have them, but sometimes you have a different kind of application or different kind of process. And in Java 13, with JEP 350, a new feature was introduced that now application could automatically save its data on exit. And this part actually helps us because of combination of Java and Spring features. How can we use AppCDS in our application? It's only 2 steps, actually. First of them, add with this argument to JVM -access archive classes at exist and put a path to your archive somewhere. And the second one is a Spring argument. Spring context exit equals on refresh. What the second one does is when your application initializes everything but lazy beans, it closes itself automatically. It exits, and the previous Java feature saves everything to a JSA archive. And we can actually reuse it. There are a couple of caveats. First, we have to use the same JDK. It means that we cannot, I don't know, create an archive with Tamarind and then reuse this archive on Liberica. It won't work this way. You have to use the same JDK. The second, you have to use the same JVM arguments, which is important part. You cannot change settings of your garbage collector. It suddenly changes your class path, and all the behavior is different, and JSA archive is not applicable anymore. And it becomes even better if we add this one small property. Spring.aot.enabled equals true AOT, sorry. Because it, as I already said, it removes some reflection from Spring. It moves this dependency tree resolution to a compile time, and we can save the whole tree of beans to the JSA archive. It means that we actually save time on dependency resolution on the consequence starts. How do we do it? It will be kind of huge Dockerfile, but I will try to show it a little bit like a small thing. So we have almost the same last stage of the build, where we copy our layers to image, and then we run it. But we have to change GRE to GRE with CDS support. In our case, it's called GRE CDS Slim. The next thing, we have to add one more instruction to a Dockerfile. We have to perform this test run of our Spring application, which is basically just adding a couple of arguments to our launch of jar launcher. And then we have this very simplistic entry point. It won't be that simple anymore, because we have to pass Spring AOT enabled equals true for Spring to read its AOT precompiled classes. And we have to point Java where our archive is located for it to try to restore its state. What does it cost us? It costs us a lot. It costs us like 81 megabytes, which is not small at all. It means that on each pull and push, even with an optimal Docker image configuration, we will have 81 megabytes. Well, as we said, we cannot have all the nice things at the same time. We have to sacrifice something. Here we sacrifice some traffic and some disk space for better startup. And we can save startup. Well, in a perfect world, it will be like 50 to 60%. With Project Laden, I won't be talking about it today, but we can probably cut up to 80% from startup. And for most companies, it's more than enough. And for most customers, I would say, because cutting like 5 seconds to 1 second is actually very good. But what if it's not enough? Then you can use project which is called CRAC. And this is the part not supported, but all JDKs, Liberica definitely supports it. Some other do not. CRAC stands for Checkpoint Restored coordinate restore checkpoint. I have very long explanation here. You probably are not interested in it. The basic idea is when the application is started, we make the memory snapshot and we save it to disk. And the next time when the application has to start up, we just read back from disk to the memory. And our application continues to run from the same place, which is very cool. It can be very fast. How do we use it? In a perfect world, it should be something like that. We should use CRAC supporting GRE. Then we have this small additional argument minus XX CRAC checkpoint 2, for example, /checkpoint. Then we copy our jar from the previous build, from the previous stage to our runner, and we copy the checkpoint. And then we would just need to run this image, and it would start in like 50 milliseconds. Reality is not that fun, because checkpoints are only supported in Linux, and they actually require some privileges to be performed. Not like all the privileges in the world, but some of them. And it's impossible. And in the previous scenario, we would get this exception, native checkpoint failed. Let's try to quickly fix it. But it will be dirty, I'm sorry. First way to fix it will be very dirty. We have to use experimental features. You can see this comment on the top. We have to add syntax equals docker/dockerfiles 1 labs, which clearly says that it's a lab feature. Then in our run, we should add this argument, run security unsecure. When your company will see this, they won't be happy and they will ask a lot of questions, obviously. I would do the same too. And also, this part will fail because Docker expects that everything exits with a code 0, but this one will exit with a code 137. And to work it around, we have to add double pipe true for it to be always successful, which is a bad thing to do, actually, because what if it actually failed, not because of CRAC? And that's not all the arcane magic we have to perform, actually. We have to create a new builder on our machine, which will be insecure, and it says it right here, allow insecure entitlement, security insecure. Again, our company probably won't be happy, and we'll give it a name accordingly, insecure builder. And then we will have to use this insecure builder to actually build our thing with our custom Docker file. And at this point, yeah, we can kind of run this application without issues, but we have to add one argument called ---- privileged. Nobody will be happy about it. It works. It's dirty, but it works. I have a... Yeah, sorry. This is not all. In my case, it started up in 2/10 of a second. Usually, it was just a random screenshot. Usually, it starts up for me in like 10 milliseconds, but obviously it depends on things. It's still extremely fast compared to 5 seconds I usually have for this application. So is it a good solution? Yes, if it works, is enough for you. For me, it's usually not. And if you need more predictable and maintainable thing, then probably we have to look for something better. Something better will look something like that. We have to build jar file of our application in whatever way we want, with Gradle, outside of Docker, inside Docker, on the other stage of CI, whatever works for you. Then we have to create a Docker file, which will run in entry point our application, and we should run this Docker with 2 capabilities enabled, ptrace and checkpoint restore. They're self-explanatory. To make a checkpoint, you need to know what your application uses. That's why you need a ptrace capability. And to call a system checkpoint restore function, you actually have to have capability to do it. It's not that scary as those previous one with insecures everywhere. Then we crack it, then we call, sorry, I didn't add animation here. As a second step, we call docker exec and call jdk.checkpoint on our application. In library images, it will always be process ID 127. On other images, it can be something different. At this point, our application will finish, and we can commit it like this: docker commit, and then pre-crack our name of running container, and to the new tag. Now we can run this. I call it here post-crack here. This image post-crack with one privilege, cap checkpoint restore, which should be probably fine. It also has some minuses, cons. Prosa, it doesn't require any arcane magic. It doesn't require experimental functions or capabilities. It doesn't require insecure builders. It's very predictable. Well, it's simple, kinda, but it will be organization specific. You cannot do everything in one Docker file, which does everything for you, as we did for CDS and for usual builds. And it requires more step, obviously, because we need to commit something and then to put something. And of course, I couldn't not mention native image. Native image also gives you amazingly fast startup times. To build native, you probably all already know, but I just have to say that in our case, we use library CRAC, which stands for Native Image Kit. We just call Gradle W native compile on our application. But here's a caveat. You remember about this huge application I was talking about? It was like hundreds of thousands of lines of code. It just won't compile with native image. It's too big. It would take too much memory and too much time. So for some bigger monolithic applications, it won't work. It's a probably very good solution for microservices, though. And then everything is simple. We just take a very basic Linux image. In our case, it's Paketo, and we copy our native image from builder to runner, and we just run it in our entry point. That's simple. It will be very relatively small. Our Paketo Linux weighs around 4 megabytes. Native image weighs whatever it weighs. Let's say it's 120 megabytes. I also have to say that this works currently in the GraalVM team. That probably it will be simpler several years down the line or several months down the line. I don't work there. I don't know. To build bigger applications, monolithic applications, you will probably be able to build something like libraries you reuse inside your application, and then probably native image will be a best solution you can find in the market about both startup time and build time, or at least balance of them. And now, at this point, we actually have all the flavors of ultimate Docker images I can think about. Let's summarize it quickly. If you are okay with your current startup time, just please use layers for faster deployment. Please save some disk space. Please, we and Spring team work together for you to have better experience. If you need to cut some time from your startup time, you can use CDS. And when and if the project Layden is released, you would be able to cut even more time. If you need a lightning fast startup, please use the project CRAC. It brings some compromises, or either more complex build or insecure builders. And you can also use library CRAC for lightning fast startup if the application is not too big for it. Thank you very much. That's all I have for you today. And we have time for one question, I think. You can follow me, yeah. Yes, please.
One generic question.
Yep.
Very often we use plugins. We use either Git plugin or Spring Boot plugin to build the images.
Yep.
What is, from your point of view, criteria when, say, the stuff with Spring Boot plugin with a buildpacks is not good, and I switch to write my Dockerfile and apply this optimization what you're
So the question is, we use plugins during our build. How do we tackle plugins during our build? Do I understand? Did I get it right?
it's more what is the side, what is the criteria to refuse from the plugin and apply the Docker file with some optimizations? What is the criteria?
Uh, yeah. So how do we understand if we need to apply a plugin, or should we use some optimizations? It's your business. You're always the only criteria you have is your your business scenario. What sacrifices you want to make to achieve some goal? Can you get everything together? Can you at the same time use plugins and use optimized builds? It strongly depends on your case. If we want, my time is totally up, but we can discuss it later outside. Thank you very much, folks.
All systems are nominal. Initialize Genesis